All right, this is Mr. McMurray, and it is Friday morning. The weekend is almost here. All right. Anyhow, getting on to a thing. Let's review a little bit about what we talked about last time. All right, here we go. Maybe not. Thermal energy. We said thermal energy is actually a type of kinetic energy because the actual molecules in it are moving faster. Therefore, it's a type of kinetic energy. Basically, the hotter the object gets, the motion of the molecules also increase. If it gets colder, then they go slower. Okay, and so it kind of goes back and forth there. That makes sense. Sound energy, we said, is when you have vibrating molecules. Okay, and so it's also kinetic energy because the atoms are vibrating or moving. If you talk really loud like that, they vibrate a whole bunch. If they talk real soft like this, they just... Okay, so the amount of movement or kinetic energy, once again, relates to the sound energy. All right, and then we have electric energy, which is basically the flow of electrons through a wire, all right, from one atom to another, and it has to be in a circuit so you don't run out of electrons, so they just keep going around and around, kind of like a NASCAR race, unless someone crashes or something, which does liven things up. But anyhow, but there you go. It's just moving, so it's also kinetic energy. Now, potential energy is different than all these different types of kinetic energy. So we had kinetic energy, which is things in motion, and that also includes things like thermal energy, sound energy, and electrical energy. Now, potential energy is a little different. Potential energy is energy that is stored, and therefore it has the potential to be released. Now, we said normally, we talk about this, we're talking about something up in the air that has potential energy to fall, okay? And it would fall because of what force? Well, it would be gravity. And so it is called Gravitational Pe, or GPE. That does not mean gravitational physical education or anything. Although I guess if you climb things and fall off, you could demonstrate that in PE. But that's probably not recommended. So these are energy stored by objects that are up above the Earth's surface and have the potential to fall. We talked about the pendulum, and as it's up, it has the potential to come back down. So it gains potential as it goes up. As it comes back down, it loses potential, but it gains kinetic and so forth, back and forth, back and forth. Okay? Now, as the object's height increases, then, the higher it is off the ground, as I said, like a pendulum as it goes up, then it's also going to get more gravitational potential energy. Okay? Because the higher it is, the more potential it has to fall back down. All right. Now, it also has to do with the amount of mass of the object. The more mass the object has, you have a bowling ball up here and you have a baseball right here, the bowling ball has more potential energy because it's going to have more kinetic energy, once again, because of the mass as it falls. It will accelerate at the same rate as the baseball, so they'll have the same speed, but because, once again, the bowling ball has more mass, it's going to have more kinetic energy once it starts moving, so therefore it has more potential when it's sitting up there. All right, that kind of makes sense. Now, the formula for gravitational potential energy is equal to mass times acceleration of gravity, which is 9.8 meters per second squared. All right, mass times the acceleration of gravity times the height. So there you go. The mass can change, the height can change. As long as you're on Earth, the gravitational acceleration is going to stay the same. Now, if you're on the moon, this number would be a lot lower, about 1/6 of that, which would be about 1.6 or something meters per second squared. Okay, but that's on the moon. All right, so anywhere on Earth, this is going to be the 9.8 meters per second squared. That's little g, or the acceleration due to gravity. All right, now that is the only potential energy that we will calculate because it actually has a formula. But there are several other types of potential energy. All right. The most common kind is what we would have in a rubber band, for example. And in a rubber band, we have elastic potential energy, or EPE for short. All right, and these are energy that is stored in objects that can be stretched, like a rubber band, a balloon. When you blow it up, it stretches out. Or that they can be compressed, like you push a spring together. It has potential, so as soon as you let go, it can spring back open. Okay, and so that would be an example of elastic potential energy. All right, so anything that can be stretched. Elastic, by the way, means not that it can be stretched, but that it will snap back when you let go of it. Okay, and so elastic potential energy, anything that can be stretched, like a balloon, whatever, or a spring, or something like that. All right, that would be elastic potential energy. All right, then the last potential energy is chemical potential energy. Anytime we have two chemicals joined together or atoms joined together, then there are chemical bonds that hold them together. And it takes energy to hold chemicals together. That's why we have to add energy to build chemicals, like our bodies. We have to eat food so that we can build all these chemicals and join them together to build our body materials out of it. Okay? And it takes energy to hold all these atoms together. Anytime we break those atoms apart, then they're going to release energy. All right, if I burn a piece of paper, I'm releasing all those bonds that hold it together to make paper. And as it changes into carbon dioxide and water vapor and carbon ash and other things that are left over, it takes less energy to hold those new chemicals together. So they release a lot of that heat. And that's what fire is. It's the energy that they're releasing that used to be holding the paper together. All right. So energy is stored in the chemical bonds that hold the elements in the substance together. Now, this is not the stuff that holds the atom together. Okay, the nucleus has some very strong energy that holds it together. That's something different. We'll get to that. But for now, let's just talk about chemical energy. Chemical energy is between atoms that join together. It's relatively, compared to the nuclear power we'll talk about later, relatively small amounts of stored energy in there. All right. Generally, when you make a new bond, it's going to store energy. Okay. If you break a bond, it's going to release energy. There are some exceptions to that, but generally, to bond something together, if you have two atoms that are sitting here, now you're going to stick them together, it's going to take extra energy. You have to add energy to make that happen. And when it does, it stores that energy in the bond. All right. When you break the bond, it's going to give off energy. All right. All right. Light energy is energy that's carried in rays of light that can travel across air or empty space and is called radiant energy. Okay, radiant energy, it's what we call electromagnetic radiation, which means but it goes up and down, little particles that do that. And so this could probably be considered a type of kinetic energy because you have a wave moving through space, or ray. Sometimes called a ray, sometimes called a wave, moving through space. And so that would be called radiant energy because it radiates or moves in rays through outer space, and it can go through outer space, okay, empty space. We'll talk more about that later. And technically, this type of energy could also include things like radio waves, microwaves, ultraviolet. They're basically the same thing. It's just a matter of how much frequency they have. The frequency that we can see, we call light. The other frequencies, we'll talk about later. And anyhow, those are it's the same energy, it's just different frequencies of it. All right. Now, the last one is nuclear energy. All right. This is the energy that's stored in the forces that hold the nucleus of an atom together. All right. And this is a much, much stronger force because atoms attach to other atoms and reattach all the time. But the actual atom itself does not tear apart. The nucleus stays together. And most of the electrons, only the outside layer of electrons can come off and hook things together. Okay, so basically it is very hard to pull the atoms apart, but you can do it. All right. In the atom, you have protons, which are positive charged. Now, if you have very many protons, they're all positive. What are they going to do to each other? Well, they're going to repel each other, go off in all directions. So there are neutrons, which are in between the protons, and they kind of act like spacers, and they also help kind of glue it together and hold it together with what we call the nuclear force, strong nuclear force and the weak nuclear force. Right now, let's just worry about that. But the nuclear force is what holds them together, and it's very, very strong, okay? And normally, we can't break that, okay? The only way we can break that is when you get really big atoms like uranium, which has 92 protons, and then it has, I think, like 140 or so neutrons, okay? And so you've got a big, bulky nucleus, and it's not very stable. It's trying to hold all these together, and we can, if we make a small bomb go off, we can split those atoms and make them break apart. When we break that nuclear energy, it releases enormous amounts of energy. Okay, and what happens is if there's other uranium atoms, one splits, it sends off neutrons that hit three other atoms and make them split. Those three send off three more, which make 9 atoms split, and you get this chain reaction. And that's what leads to eventually the mushroom cloud or the nuclear power plant where you can have all this electricity and everything going on. Okay, so we can use that energy for good electricity or maybe good or bad, depending why you're using it as a nuclear power. There's a lot of debate, of course, about when is it okay to use nuclear power or not, but we're not going to get into that right now. But that's nuclear power. That's not the same thing as chemical potential energy. Okay, this could probably also be considered a type of potential energy because every nucleus has this energy stored up. Only in a few large unstable atoms are we able to tap that and to break it apart and use that energy, but it is there and in every atom of those kind. All right, so we are going to stop our bank route right there. Next week, probably on, Tuesday, we'll probably have a quiz over all these notes, so by all means, feel free to study up on these. And we will see you on Monday. Have a great weekend.